Hey, welcome to my channel, Electric Wisdom. My name is Sheehan and I'm a master's degree student in electrical engineering. I've been studying electricity for a long time, and today we're going to talk about what is electrical resistance. What is electrical resistance? How can we use it to our advantage in electrical circuits? How do we calculate it? Well, that's exactly what I'm going to show you in this video. I'm also going to talk to you about actual physical resistors and how to read the value of a resistor. And when we're done, you're going to have a much more thorough understanding of what electrical resistance is. All right, let's go. Welcome to Electric Wisdom. Today's topic, resistance. In my previous video, I discussed current flow in terms of a husband and wife, Mrs. and Mr. Q, who represented, respectively, an electron and the absence of an electron, a hole. If you want to gain a better understanding of current flow, I have posted a link to my other video titled Current Flow, What You Need to Know, below this one. So what is resistance? Well, electrically speaking, resistance can simply be defined as an opposition to current flow. In terms of everyday life, how difficult will it be for Mrs. Q to return to Mr. Q after they have been separated? Let's look at some examples. In our first example, Mr. Q is in the living room and Mrs. Q is in the bathroom. Once Mrs. Q is finished in the bathroom, she wants to return to Mr. Q. But let's say the middle of the house has collapsed due to a falling tree outside. In this case, there is no path for Mrs. Q to return to Mr. Q in our closed system, the house. And so we say Mrs. Q has encountered infinite resistance. There is no way for her to get to Mr. Q. In electrical circuit diagrams, we can represent infinite resistance by either an open circuit or an open switch. In our next example, let's say that there is nothing in Mrs. Q's path to Mr. Q. Ideally, we can say that Mrs. Q doesn't even have to overcome gravity and friction to get to Mr. Q. In this idealized case, we say there is zero resistance. In electrical circuit diagrams, we can represent zero resistance by either a straight line or a closed switch. This is what we call a short circuit, as opposed to the open circuit infinite resistance of the previous example. Now, it's important to remember here that there's no such thing really as infinite resistance and zero resistance. These are idealized cases, and we know that the world is not ideal. We have to understand that we can't have infinite resistance and zero resistance. We can only assume that very high resistances are infinity and very low resistances are zero. So now we understand a little bit more about what electrical resistance is, but how do we measure it? Every material has what scientists call a coefficient of resistivity, as shown here in this chart. This is just to show how resistive to current flow a material is. The higher the coefficient of resistivity, the more resistive it is. An important side note to make here is that the inverse of resistivity is conductivity, or the ability of a material to conduct electricity. This shows that conductivity is inversely proportional to resistivity. As resistivity goes up, conductivity goes down by a proportional amount, and vice versa. The coefficient of resistivity is analogous to how cluttered Mrs. Q's house is. If her house is very cluttered, we can say that her house is more resistive to her traveling through it, and vice versa. The equation to calculate the resistance of a given material is given by the coefficient of resistivity times the cross-sectional area of the material the current is traveling through, divided by the length of the material the current is traveling through. This actually makes a lot of sense when we think about Mr. and Mrs. Q. If the length that Mrs. Q needs to travel goes up, then it will be more difficult for her to get there. But if the area she is traveling through increases, then it will be easier for her to maneuver and therefore the resistance is lower. Please keep in mind that Mr. and Mrs. Q are a very simplified example of current. Mrs. Q represents one electron, whereas current flow comprises an almost unfathomable amount of electrons. So when we think about the area that current needs to travel through, it also makes sense to think that if there is less area and you're trying to pack more electrons through that area, you simply cannot get as much electrons through. It's rather straightforward to represent our simple example on a large scale with Mr. and Mrs. Q all separated and longing to be together again. And one of the most important rules we must be sure to remember in our electrical studies is that just like humans, current likes it easy. And so it will always take the path of least resistance. Okay, now let's take what we learned theoretically and apply it to the practical. Let's talk about resistors. This is what a real resistor looks like. We can see that our resistor has 4 colored bands on it. These bands correspond to a color code table that allows us to determine the value of the resistor in scientific notation. To give you a good example, we will use our color code chart to determine the value of our current resistor. The number of lines on the resistor may vary depending on its value, but you can always be sure that the last 2 are the multiplier and the tolerance. Knowing this will tell you how many digits the resistor value will have. In this case, we know that this resistor has 4 bands, and therefore will have 2 digits. The colors are yellow and red, which, following our chart, corresponds to the number 42. Our penultimate band, the multiplier band, is green, corresponding to 10 to the 5th power. Our last band is the tolerance band, which is gold, corresponding to plus or minus 5%, the range that the resistor will have. Therefore, we know that the value of our resistor is 42 times 10 to the 5th ohms, or 4.2 million ohms. That's a lot. And this will fall into the range of plus or minus 5% of 4.2 million ohms, which 5% of 4.2 million is 210,000 ohms. A good example of the usefulness of a resistor is in a basic LED circuit, where we have an LED connected in series to a 9-volt battery. The small LED is rated for a very small amount of current, so if we connect it directly to a 9-volt battery, it's most likely going to burn up and not work. By adding a small resistor to resist the current flow, we can ensure that the current remains below the LED's rated threshold, and will therefore operate correctly. How this actually works in terms of the relationship between voltage, current, and resistance will be explained in my later video on Ohm's law. We can take this application of the small LED circuit and expand it to even bigger circuits. Resistors are extremely useful in limiting current flow, and therefore in protecting different types of circuitry on small and large scales. Alright, that about wraps it up for resistance and resistors. If you liked my video, please give it a thumbs up, and if I added something of value to your life, please subscribe. There's going to be a lot more where that came from, especially on basic circuit theory now, and a lot more on electrical engineering and physics and calculus in the future. I think the most important thing you could take away from this video is that resistance opposes current flow, and current always takes the path of least resistance. So if you take anything away from this video, take that. Alright, thanks again for visiting Electric Wisdom. Bye.